Lab 3, the Black Hole Lab. The objective of this lab was to use the information of a star's mass and motion to find the mass of a black hole and analyze the different forces acting on the star, which changes its momentum. The star's motion was given in a CSV file. Using Newton's gravitational force principle and the different net force components, including the components of the change in momentum, we created a computational model to find the mass of the black hole in my lab, which was 2.7862 times 10 to the 31st kilograms. Now let's talk about the physics used in this lab. There are two main physics principles in this lab, the momentum principle and Newton's law of universal gravitation. In the momentum principle, dp/dt, the change in momentum is equal to the net force acting on an object multiplied by the change in duration. Two components of momentum we observe in this lab are the momentum in the parallel and perpendicular directions of the force, shown in the equations below. Newton's universal gravitation principle states that there is a force of attraction between all masses, proportional to the multiplication of their masses and inversely proportional to the distance between the objects, which can be seen in the universal gravitation equation shown on the slide, where the constant g is equal to 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. Now let's discuss the model. The star's mass, change in time, and black hole's position, shown, were all given in the assignment and put into a model and code to find the mass of the black hole. We also include the CSV file data to include the motion of the star. Now here are the equations from the code. First, we need to calculate the velocity of the star, shown in the first equations. Using the velocity, I found the star's momentum by multiplying the star's velocity by the star's mass. Using the initial and final momentums, I calculated F net equaling to dp/dt, which is equal to the change in momentum over the change in time, which is all stated in the momentum principle. Then I found the direction of the momentum and the magnitude of the momentum, which when multiplied together gave me the momentum in the parallel direction, equal to the net force in the parallel direction. To find the momentum in the perpendicular direction, I subtracted the parallel momentum from the overall momentum, which is equal to the net force in the perpendicular direction. As I ran the code, you see as the arrows get bigger, the forces are increasing because the distance between the star and the black hole is decreasing. Then the arrows get smaller as the star moves away from the black hole. The yellow arrow represents the net force, the blue arrow represents the perpendicular net force, and the black arrow represents the parallel net force. This is the equation from my code. Using a rearranged form of Newton's gravitational principle formula, I found the mass of the black hole is equal to the magnitude of the force multiplied by the distance between the star and the black hole squared, all divided by the constant g in the star's mass. My black hole's mass is found to be 2.7862 times 10 to the 31st kilograms. Now let's answer the analysis questions. What does it mean? I was asked to discuss how the net force overall perpendicular and parallel are different from dp/dt overall perpendicular and parallel. Well, the net force affects the star's motion, while dp/dt describes the star's motion. Therefore, the net force in the perpendicular and parallel positions affect the direction of the star, while dp/dt parallel and dp/dt perpendicular only describe the star's motion in the parallel and perpendicular directions. They are also calculated differently. The net force is calculated through Newton's universal gravitation principle formula, while the change in momentum is found by using the change in velocity. What if? Imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of an observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? No, because there is no alternative gravitational force to use to calculate a new mass of the black hole. The motion of the star is unchanged and the data in the CSV file is the same as well. If there was a different path with different points in the CSV file, then you could, but in this instance we cannot. Thank you for watching.